My PhD work focused on developing a particle in cell method-based numeric model for coastal and offshore engineering applications. Today, I would like to introduce the particle in cell method. As we know, in CFD modeling, the unit method based on the grid and the Lagrange method based on the particles are widely used. Typical examples are the open form model and the SPH model. Now, while the unit methods are very efficient, they have difficulty in handling discontinuity, such as large free surface deformations of fluid flows. On the other hand, the Lagrange methods are very flexible in handling such discontinuity, but they are mostly very costly in terms of CPU time. The idea of particle in cell method is to resolve those issues in pure methods and combine the advantages of pure unit and Lagrange methods through a joint use of particles and grid. Here's an example: grid and particles. It is worth mentioning that the particle in cell method is actually very old. It was first devised in 1950s by Professor Harlow and his colleagues, but it hasn't attracted sufficient attention from the community of coastal and offshore engineering applications so far. So, how exactly does the particle in cell method work? Let's take Levi-Stokes equation as an example. According to the particle in cell methodology, the solutions are divided into three major steps. In the first step, the Levi-Stokes equation, ignoring this nonlinear division term, are resolved on the grid. Now, this can be very efficient, as any optimized numeric scheme based on the grid can be employed now. Once this is done, the information on the grid will be transferred onto the particles for the next step. In the second step, the particles are moved or advected to solve this nonlinear division term, which effectively removes the complexity of solving this term on the grid that can lead to the difficulty in handling discontinuity we mentioned before. In this step, the particles are also used to track the fluid configuration and the free surface position. Once the particles are advected, in the third step, the information carried by the particles are mapped again onto the grid for the next circle of computation. These are the basics of particle in cell method. There are, of course, many difficulties and challenges lying in this method. For example, in the third step, when we transfer the data from the particles to the grid, numeric dissipation may occur, as it is very difficult to actually reproduce data set from scattered particles to the uniform grid. Also, as I mentioned earlier, the particles are used to track the free surface position, which is much more straightforward than solving equations on the grid. However, at some point, we have to reconstruct the free surface indicated by the particles on the grid in order to solve the equations in the first step. To summarize, the particle in cell method has a great potential to become a high-quality numeric tool for coastal and offshore engineering applications, as it combines the advantages of both unity and Lagrange method. However, this method also faces a lot of challenges and difficulties, and thus require more research.